In this video, we'll look at a very basic board bring up of this LittleBrain board, which I featured in one or two previous videos. In essence, it's an update of the original LittleBrain with a different MCU and some various different peripherals to meet the global chip shortage that's happening at the moment. I would just like to show you a very simple way, once you get your PCBs back fully assembled, to check if they're working, to check all the functions of the ICs. See how we can program this STM32 F4 microcontroller with this tag connect header, and look at the IMU as well as barometer, just to check if we can get something back from them. So a very basic board bring up. So once I get my PCBs back from assembly and manufacturing, the first thing I do is just a visual inspection, just to see if I can see any shorts, maybe some misplaced components, if all components have been placed, checking all the tolerances and clearances and so on. Normally then I would ramp up my power supply, my input power supply, and then check various voltage regulators. With this board, this is only powered via USB, via this micro USB connector. So I'm going to check for shorts first, checking, plus 3.3 volts and ground, my 5 volt input and ground and so on, to see if there are any shorts, and then continue. Now I've already done that and I've found that there are no shorts on this board, so I'm just going to go ahead and plug in this USB cable and hope nothing explodes. And don't plug the other end of this USB connector into something you value, because this could get destroyed if there's some sort of current surge or God knows what. So I plugged in my USB cable and you can see nicely there's a green LED, and that's already a good sign. I also don't smell or see any smoke, so that's always great as well. Joking aside, on most PCBs this is the first good indication that something's working. This LED actually indicates that there's some sort of output voltage at this tiny regulator over here. So something seems to be working. I'd like to thank Neil from Tag Connect for providing the headers and connectors for this video. And you can see I featured this in a couple of videos before. This Tag Connect pogo pin is used to program this device via serial debug. So instead of using a dedicated connector, which takes up more space than this tiny footprint over here, as well as using an additional part, which is the bill of materials, I can simply use these pogo pins to then connect them up. You can then add on a retaining mechanism so you don't have to hold this the whole time, like so, and this just plugs in the back. There's also different versions of this Tag Connect header, and these days this is my preferred way of programming these devices because I can just plug this in, I don't have to mount an additional header. And the other side of this header, which is this adapter board, then plugs simply into my ST-Link version 2, and then I can use this to program. Thank you very much to JLCPCB for sponsoring this video. The LittleBrain PCB was manufactured and assembled by them. In recent news, it turns out that JLCPCB, in addition to their own parts catalog, also now supports global parts sourcing, which means you can pre-order parts from Mouser, DigiKey and so forth, which can then be assembled by JLCPCB. If you'd like to have the LittleBrain PCB assembled for yourself, you can go to my GitHub repository at github.com/pms67 and navigate to the LittleBrain repo. You can find all of the Altium design files, as well as assembly and Gerber PCB files over there. A huge thank you also to Altium for sponsoring this video. If you'd like to get a free trial of Altium for yourself, you can go to altium.com/yt/Phil's Lab. In a previous video, you can follow the design steps for this LittleBrain board and how to use Altium in detail. Here we are now in Altium Designer, and I'd like to give you a brief overview of the hardware we'll be writing our very basic firmware for. Let's start with the power supply. We get 5 volts from the USB connector, we perform some light filtering, and then we pass that through to our linear LDO regulator, which gives us our 3.3 volt output, and we already saw this green status LED. The second page of the schematic then gives us the microcontroller and peripherals section, so we have this STM32 F411 microcontroller, so a fairly powerful little device, and here we can see the pinout. And this pinout is something we'll need for the firmware, of course, to tell us where we have the SD card signals, USB, serial debug, and so forth. We also have a little test LED or status LED connected here, and we'll be flashing that later as well. We should make note of the clock frequency at 16 MHz because we require that for our clock setup. And of course we have our USB connector where the data lines feed into the microcontroller as well. The remaining page is filled with connectors, so we have our serial debug tag connect header over here with protection, our GPIO connector, as well as our SD card connector. Finally, we have the sensors page, so we have one inertial measurement unit, which is on the I2C1 bus, and we also have this interrupt pin as well. I've already denoted the I2C address, which I found on the datasheet, and we'll look through that later as well, at 0868. We also have a barometric pressure sensor, so we can use that, for example, to determine altitude. This also has an I2C interface. I've put that on I2C2, so a separate I2C bus. This also has an interrupt pin, and I've also denoted the I2C address, which we'll need later. So all in all, a very, very simple system. We have our main microcontroller, which is clocked via this HSC high-speed external crystal, inertial measurement unit, programming interface, SD card, GPIO header, barometric pressure sensor, and USB. Let's move over now to bringing up this board, writing some very basic firmware. The way I'm doing that is via STM32CubeIDE, which is a free development environment provided by ST Microelectronics for the STM32 line of microcontrollers. So if you'd like to follow along, if you have your own board, I'd recommend to just download it here, and let's move over. So here we are in STM32CubeIDE. This is the default view you'll see. All we need to do is create a new project. So I'll go to File, New, STM32 Project. Once you've clicked on New Project, you will see this view where you can type in your part number of your STM32 microcontroller, or if you have a development board or some other type of pre-made board, you can choose that here as well. We'll choose our microcontroller, and remember that was an STM32 F411 CEU6. So I can click on this here, and I can also see what package it is, how much flash and RAM I have, and so forth. Then click Next, and we'll just give it a default project name. I've just called it LittleBrain++ test firmware, and I'll just keep it at C for the moment. Then I can just click Finish and let it generate. Once the initialization is complete, you'll see a view quite similar to this one over here. And this is the top view of our package. You can see all of the pins around the package, and you can also immediately see what they do by hovering and then clicking on them. So for example, this pin might be used as a GPIO input, GPIO output, whereas this pin down here could be used as an ADC or timer channel or UART part. So what we need to do with our board bring up, and this is probably something you should have already done before you designed the hardware or while you were designing the hardware, is take everything from Altium or KiCad or whatever software you're using and import all those pins in here. So if I go to my MCU section, I will see, okay, PA11 needs to be USB-D- and PA12 has to be USB-D+. So if I go back to STM32CubeIDE, I can say, okay, click on this one and say this has to be USB-D- and this one has to be USB-D+, which is kind of a slow way of doing it. The other way of doing it is just going on these tabs over here. So clicking, for example, on connectivity, clicking on USB, and then enabling that as a device only. And this will then automatically enable these two pins. So this is what I'm going to do for the USB, for the I2Cs and so forth, taking my pinout from this document over to STM32CubeIDE. Now keep in mind, when you design hardware, you will usually start with STM32CubeIDE, define your pinout here, and then take that over to Altium, or whatever EDA software you are using. So far I've set up my USB differential pair, I've set up I2C1 and I2C2 according to my pinout. You can also see I have this GPIO output here, and this is actually the output to my LED. Now just calling it GPIO output isn't very helpful, so I'm going to right click and enter user label and just call it LED. You can do that with almost all of the pins, right click and give them sensible names. This is almost enough to start with, but remember we also need to program this device, so we need to enable serial wire debug. The way we do that is go to sys, then debug, and I'll use trace asynchronous serial wire. This gives me my serial wire clock and my serial wire data pin, as well as this serial wire trace pin, and this is used for monitoring live variables, plotting, and so forth. We won't be using it for this video, but because we'll hopefully be doing more firmware updates, I just enable this by default because I might be using it later. Another thing we have is actually a high-speed external crystal. I can go to RCC and then enable my high-speed crystal ceramic resonator, and this appears to be on PHO and PH1. You can also see we have a little cross up here on the clock configuration section. Here we are now in the clock configuration tab, and we have to change our input frequency because we're using a 16 MHz high-speed external crystal. So let me change that. Make sure our clock source, our PLL source, is set to the high-speed external. The STM32 also has an internal clock, but that isn't entirely accurate compared to, for example, this external crystal. And I will just choose my clock frequency to be a multiple of 16, so let's say 96 MHz. Then click enter, and it'll try to find a solution to set all of the PLL values, make sure all of the constraints are met. That was pretty quick, so you can see it set all of the PLL values, it set all of the clock and peripheral clocks over here, and made sure that our system will be running at 96 MHz. So we can go back to our pinout and configuration, and this will be enough to start with. I know we have more peripherals, we have an SD card, we have interrupt pins and so forth, but remember, we just want to test the very, very basic functionality of our board. And to start with that, we'll probably just start with LED, we'll see if the USB is working, and see if we can talk to the I2C devices on this board. So once you're happy with that, you can just click save, and this will then generate code for you. So it'll import all these hardware abstraction layer drivers, and then we can get started once this has been generated. So I'll click yes, and let it do its thing. You'll then be presented with this view, and you can see it's already generated a fair amount of code. The left tree here, I can see it's generated all of these files for us, and this program would pretty much run directly on our microcontroller, but of course not do very much. Let's just go through what it's created. It's created our various handles for the I2C, for the USB, as well as our int main function where everything is being set up, and then we have our main while loop. So what I usually do first with a board bring up is just simply see if my connection works. So I've plugged in my serial wire debug via the ST link and via my tag connect header, and I power the board via USB. So what I can do is then click on this bug, and this will upload the code and go into debug mode. It'll build the project, and then we have to edit the launch configuration. You can see there's various items we can choose, for example, what debug probe we're using serial wire debug or JTAG and so forth. And most of these settings are pretty much fine to keep default. So just click OK, and it'll try to launch. You can see it's waiting for the debugger connection. Let's switch the view. It says download verified successfully, and that is a great sign. And it's already stopped at our first breakpoint, which is the first point in int main. So this already looks pretty good. We know that the serial wire debug link seems to work. We can talk to our microcontroller. So this is already pretty promising. So I can just click on run here or resume, and now my code is running. Essentially now it's just stuck in this infinite while loop, not doing very much. So now that we know that we can upload some form of code, let's see if we can flash an LED, just to start with. To do so, I've stopped the program, and we'll just have in the while loop, we'll have a delay, and then we'll just toggle the pin. There's a HAL function called HAL GPIO toggle pin, and if you control click, you can actually go to that function definition, which is over here in the hardware abstraction layer driver, and you can see we need some sort of GPIO pin bank, and we need the GPIO pin itself. Now, because we've renamed this pin, remember we've renamed it to LED, we need to do a bit of searching, and if we scroll down to MX GPIO in it, we can see this is the LED GPIO port, and this is the LED pin, and behind that is actually some sort of number, as well as behind the GPIO port. So I can copy this, and then put that in my function. Now, if I just run this, this will run at maximum speed. We won't actually see anything flash. So of course I have to add some sort of delay. The way to do that is via our HAL delay function, and this takes milliseconds as an argument. Let's just say every half a second, so 500 milliseconds. So I can then compile my code, and then I will just upload it. I can either use this debug or just run it. So as usual, waiting for the debugger connection, and download verified successfully. So now let me switch the camera view and show that this LED is flashing. So here we have the LittleBrain connected, and we've just uploaded the LED flash program, so that seems to be working. At least we can drive an LED, and we can upload code to this board. Now that we've verified the programming and that we can at least toggle an LED, let's try out the I2Cs. The reason for testing out the I2Cs next is to see if the inertial measurement unit works, or at least if we can talk to it, as well as the barometric pressure sensor. The way I typically test this is by just probing, for example, the whoami register, and pretty much every I2C peripheral will have some sort of self-test or whoami register, which gives you a fixed value back if you probe it. And we'll do that both for the inertial measurement unit and for this sensor as well. So remember, the IMU is on I2C1 and the other sensor is on I2C2. Now I've opened up the MPU 650, which is the inertial measurement unit register map, and this gives us details of the various registers available in this device. And if we see register 117 is the whoami register. And this is really useful for board bring up tests like this. So we can address it at register value 0x75 in hex, and it turns out that the default value of this register is 0x68. And 0x68 actually happens also to be the default I2C address of this whole device. So we're going to try and read the I2C address at 0x68, and then also the register address at 0x75, and see if it matches this value. And this is a very, very basic way of testing, first of all, if the I2C communications work, and also if we can talk to this device. So going back to STM32CubeIDE, there is one function we'll be using in a polling method to test the I2C. There's no point in doing DMA or anything fancy with interrupts yet before we've even verified that we can talk to this device. The function we'll be using for polling or for reading a register value via I2C is the I2C memRead function, also available in the HAL. So I've typed it in here, and I can control click as usual to follow it through. So once I've followed through this function, you can see it's I2C memRead, and it reads an amount of data in blocking mode from a specific memory address. It returns the HAL status type def, and this is either HAL OK, HAL busy, or HAL error, and this is also an indication if this bus works. If we get HAL OK back, that is a pretty good sign. Now the arguments this function takes is first of all the I2C handle, and remember we have I2C1 and I2C2 for the IMU and for the barometric pressure sensor respectively. Then we have the device address, which is the actual I2C address, and then we have the mem address, which is which register we want to talk to or read from. Then we have the mem address size, for example 7 or 8 bits and so forth. And then we have a pointer to where we want to store the resulting register values. We can read more than 1 byte at once, for example, and here we have how many bytes we want to read, and this is the maximum time we would want to wait for this transaction. So let me copy this and let's fill in the gaps. So I'm going to paste this function prototype over here, and then we just replace things as we go. So first of all, that I2C type def has to be passed by reference, and that was I2C1. Then the device address is something we get from the datasheet. Alternatively, I like to write that underneath in my schematics, and I found that to be 0x68. With this hardware extraction layer, this is actually a 7-bit device address, so I have to left shift this 8-bit device address by 1 to get a 7-bit device address. Then our memory address was the address of our register, and remember this was 0x75 in hex. So that's 0x75, and the mem address size is actually already defined by the hardware abstraction layer, and I'll just copy that in. It's I2C mem add size 8-bit. We want to read 1 byte from this memory address, and we need some sort of variable to store our data. So let me just create that up here, and that's going to be a type uint8t, so 1 byte of data, and I'll just call that reg data, register data, and I have to pass that by reference. I just want to read 1 byte, and timeout you can put, I don't know, let's say 100 milliseconds, for example. Now we also have this return value, which is the HAL status type def, and I'll just create another variable just so we can check what the status is. In combination with this LED toggle code, I'm calling this memread function. I've passed in my I2C handle, my device address left shifted by 1, my register address, 8 bits of data, where I want to store my resulting register information, 1 byte of data, and the timeout. And of course, this will be called every 500 milliseconds. So let me just upload this to my board. So it's downloaded successfully to the board. I can just click resume for now. And then anytime I want, I can just set a breakpoint here, for example, double clicking, and you can see it stopped. Now I can either hover over certain expressions, for example, status, and I can see I've got a value of HAL OK back. So this is great news. The transaction must have succeeded in some way. Now we can check our register data information. You can also see on the right here, that's already apparent. Register data and status is shown over here. Alternatively, I can also just hover over and it has a decimal value of 104, and in hex, that's 0x68. Going back to the register map, you can see the default value of this register is 0x68. So it looks like things are working. We can read register values, which probably means we can write register values as well. I2C bus seems to be working, and we can talk to the device. We won't go any further with this, and we'll just do the same thing for the barometric pressure sensor. Remember, this is a very, very basic board bring up. So next, moving on to the digital pressure sensor or the barometric pressure sensor. This was connected on I2C2. First of all, let's just find the address in this datasheet. So I'll type in address, and you can see the sensor's address is 0x77 by default, or 0x76 if the SDO pin is pulled down to ground. So going back to the schematic, I've actually pulled the SDO pin high, which means it's the default I2C address at 0x77. That's the first bit of information we need. If we go to the contents of this datasheet for the barometric pressure sensor, we can scroll down a bit and see there's also a register map and register descriptions for example, the product and revision ID, which is pretty helpful. So here's the information for the product and revision ID register, which is very similar to the whoami register of the inertial measurement unit. It's at address 0xOD, and its reset value is 0x10. So by probing this register, we can find out, okay, is the communication somewhat working, and can we get this correct value out? So back in STM32CubeIDE, I'm just going to overwrite this code because we've already used that. We've verified that we can get some sort of communication working with our inertial measurement unit. So remember, our I2C address for the barometric pressure sensor was 0x77, and we want to query register address 0xOD. But remember also it's on I2C2, so we just need to change that here, and then that's pretty much all we need to change. Note that it isn't good practice to just type in, for example, register addresses like so, just as pure values, and the device address like so. That isn't very clean. But for a board bring up, I think that's perfectly acceptable if you just want to quickly test that the board functions are working. So now let me stop this program and then reflash it, and let's check it again. So now I have my breakpoint set again. I can just press play or resume, and now I can read that status is HAL OK again, so that's good, so we can have some form of communication on the I2C2 bus, and our register data seems to be 0x10. Going back to the datasheet, 0x10 is exactly the ID number we wanted. So in a very, very basic way, we've verified that we have some sort of communication on both I2C1 and I2C2 with our various peripherals, and we're getting sensible values, at least for these registers, out. Of course, now you could go a bit deeper and actually try and read sensor data, so verify if, for example, the angles are correct, if your altitude estimates are correct, and so forth. But for this very brief video, we won't be going over this. But now let's move over to the USB side of things. The last thing we'd like to look at for our very basic board bring up is USB. We can use USB to stream data, for example, and this is useful for debugging if we want to do something, log something to the console, if we want to stream audio, for example, and so forth. We already set up our USB differential pair over here. However, STM32CubeIDE and the hardware abstraction layer offers some more helpful things. If we scroll down to middleware, back in this configuration panel, and click on USB device, we can actually choose a class for our device. So this could be audio, could be a communication device class, or virtual COM port, and so forth. We'll use a communication device class or virtual COM port, and this allows us to send, for example, text data or binary data back to the host, and from the host to this device. So we can enable that, and that'll then include an additional driver, but we also need to go to the interrupt controller over here and enable USB on the go interrupt for this to work. Then you can click save and it'll recompile and create new code for you. Before we can get started with this, however, we need to add a couple things for this to actually function, which is a bit annoying, to be honest, that it isn't implemented automatically. The first thing is we actually have to include this new CDC driver, this communication device class driver, usbd_cdc_if.h in our main.c file, and save that. What we also need to do is in our project tree over here on the left, we need to find our USB device folder, which is now newly created, click on app, and then find usbd_cdc_if. I've already filled in some data here to make this work, but normally this actually does not come with this data. It could be that without this additional information put in here, it might work on certain systems, maybe older Windows systems or Linux or something else. However, to make it work in pretty much all cases, you need to add these lines over here, so sort of line coding, essentially to tell the host or whatever it's connected to that it's running at a certain baud rate with certain stop and parity bits and so forth. This is the first change you have to make to this USB CDCIF file. Make sure that any change you make is written between begin and end statements. For example, if you make more changes in this file here, and then save, and the code gets recompiled, you will lose anything that isn't between begin and end blocks. So this is the first change, and I'll leave that in the description box below. And the second change is in the CDC control FS function. If we scroll down, I've added this line and this line. Again, I'll leave this in the description below. Once you have that, you should be able to get USB up and running. The way we do that is go back to main. If we go to our main function, we can see STM32CubeIDE has already initialized our USB device, and I've added some additional code. We still have our old I2C memread as well as our LED functions over here, but I've added this code, these two lines in between. Essentially, I've created a buffer, and this buffer has a certain length or the amount of characters we want to transmit. I'm using the SNPrintf function to essentially write data into my buffer. I'm sending my register data back over the USB virtual COM port. SNPrintf is pretty nice because the resulting amount of characters that actually been written or the buffer length is then stored in this variable. I need this because my actual CDC transmit function is called CDC_transmit_fs, and I need to pass the buffer as well as how many characters or how many bytes I want to transmit. Then I just do my LED toggle and I delay by half a second. Then I can simply recompile by clicking the hammer up here, and then I can upload this code to my board. Once this code has uploaded, I can go to my device manager and look at ports. And you can see here, COM3 has now appeared as ST Microelectronics Virtual COM port. So this is already a pretty good sign that things seem to be working. Next, I'll open PuTTY, and PuTTY allows me then to read the data that's coming or being streamed from my STM32F4 microcontroller. I need to click on serial, I need to type in whatever my virtual COM port is, that seems to be COM3, and remember the baud rate. I can click open, and you can see I'm getting data streamed back. So every half a second, I'm getting data equals 16, and 16 was the reg data, and if you remember back, that was hex 0x10, which of course then is 16. So this seems like it's working, which is pretty cool. So we've verified USB, both I2C links, and of course the LED serial wire debug, and that this thing seems to be working. Thanks for watching this very brief overview of how to bring up a PCB in firmware as well, testing the STM32F4 microcontroller with USB, I2C, and some very basic setup. Of course, there's much more to this, and you should go in far greater detail, checking, for example, that clock speeds are correct, that you can run your buses at the maximum rate you want them to, we didn't check the SD card, and so forth. There are many, many more tests you need to do when bringing up a board, but I hope this is just a brief introduction for your personal project, just to get started and just to get the basics set up. Thanks for watching, and I hope to see you in the next video.